Welcome back, dear grade 9 students, and as I promised, here is a second training geometry exercise, and as you see, you can notice plenty of midpoints, so we are definitely gonna talk about the midpoint theorem and its converse in this exercise. And by the end of the video, there is a slide that includes a bonus information. So stay tuned and let's get ready to start with the first part. But first of all, let's see what's given. We have ABC is a triangle in such a way that AC is equal to 6 and BC is equal to 9. Also, we have that BM is equal to 3. Then the distance from here to here is 3, and since BC equals 9, what remains for MC is 6. Also, we have that E and F are the midpoints of AB and MC respectively. Then F is midpoint of MC, so we are going to get here a 3 also, and here a 3. So as if we have 3 equal parts, each of them is measuring 3. And also we have that EN is parallel to BM, and that's the key of the solution of first part, as you are going to see. Now let's start by the first part. In the first part, we have to verify that N is the midpoint of that segment AM. Now, to prove a midpoint, usually to prove that N is a midpoint of AM, usually we prove that NA and NM are equal. If we can prove them, we say that AN and M are collinear, or we prove them to say that N is midpoint of AM. But there is another way for proving a midpoint, and especially when we have a parallel. That way is called the converse of the midpoint theorem. So when we have that EN is parallel to BM, then since E is the midpoint of AB and EN is parallel to BM, then surely N is going to be the midpoint of AM. But we have to specify the triangle we are considering. So we have to take into consideration triangle ABM. So in triangle ABM, we have that E is midpoint of AB. We have that EN is parallel to BM, thus N is midpoint of AM, and that's what we call the converse of midpoint theorem. We also have to calculate NE. So to calculate NE, we just divide the side facing it, which is BM, by 2. And since BM equals 3, so as we mentioned before, BM equals 3, then 3 by 2 is 1.5, and that's midpoint theorem. So that's part 1, as easy as possible. So we used the converse of midpoint theorem to prove that N is a midpoint, and we used midpoint theorem to prove that, or to find EN, that's half BM. Now let's move to part 2, and in part 2 we have to prove that NF is parallel to AC. So again, we are going to specify a certain triangle to use midpoint theorem in. We have to take triangle AMC. In triangle AMC, N and F are midpoints of AM and MC respectively, because N is proved the midpoint of AM in part 1, and F is given the midpoint of MC. So NF is going to be parallel to AC, and NF is going to be equal to the measurement of AC over 2, and that's midpoint theorem. So that's why NF is parallel to AC. In part 3, we have to prove that triangle CNF is an isosceles triangle. So CNF. It seems that the equal legs are Fn and Fc, and let's prove that. So let's go ahead. And CF, according to CF, that CF is equal to MC over 2, because I mentioned that whenever BM is equal to 3 and MC is 6, because BC equals 9, then what remains for MC is 6, and since F is its midpoint, then MF is equal to FC is equal to 3. So FC is equal to 3. Now NF that NF, that's half of AC, and AC is given 6, then NF is also equal to 3 using the midpoint theorem. So FC and NF are both equal to 3, then CNF is an isosceles triangle because it has 2 equal sides, and that's also very easy. Let's continue what we have in part 4. In part 4, let I be the midpoint of Bn. So here is Bn, suppose here is I, the midpoint of Bn. We have to prove that MINF is a trapezoid. So we have to prove that MINF is a trap. To prove a trap, we have to prove that the bases are parallel and the other sides are non-parallel, or we have to just say it. So how to prove that MI is parallel to NF? Let's go ahead. In triangle BNF, so again we have to specify the triangle we are using. BM equals MF equals to 3, and they are collinear. Then M is midpoint of BF. Also, I is given midpoint of Bn. Thus, IM using midpoint theorem is parallel to NF. And that's what we need to prove that MINF is a trapezoid. So MINF is a trapezoid because it has parallel bases and 2 non-parallel sides. It's not a parallelogram, it's just a trapezoid, so we just have to find 2 opposite parallel sides or bases. In part 5, we have to join CN and AF. And these 2 segments intersect here at a point called J. What does J represent in triangle AMC? So don't forget that N is midpoint of AM. Thus, CN is a median relative to AM. But let's say a note here. Don't forget, we have proved that CAM is an isosceles triangle of vertex C. Or it is an isosceles triangle of vertex C since CA is 6 and CM is 6. Then CN is not only a median. Let's remember the properties of the isosceles triangle. Because N is a midpoint and C is the vertex of that isosceles triangle whose legs are equal, CA and CM, then that median CN is also gonna be a perpendicular bisector because it's a median relative to the base, and it also bisects the vertex here. But AF is just a median because it's not relative to the base, and it is joining a point or a vertex of this triangle to the midpoint of the side facing it. So AF is called a median. Thus CN is gonna be used as a median only and not as a perpendicular bisector or as a bisector. But I mentioned that to remind you of the property of the median relative to the base in an isosceles triangle. So CN and AF are medians in triangle AMC. That's why, what does J represent in this triangle? Can you remember the name of the point J? It is the centroid of triangle AMC because it's the intersection point of 2 medians, AF and CN. So J is called the centroid. What is another word for the centroid? There is another word called the center of gravity. So another word for the centroid, which is the intersection point of medians, is called the center of gravity. So J is the centroid or the center of gravity. In part 2, we have to deduce that MJ, if we draw the line MJ, it cuts AC at its midpoint. Let's justify why. because MJ passes through J, which is the centroid. Then it is the third median. So AF is the first median, CN is the second median, or CN is the first and AF is the second, never mind. While MJ now that passes through J is definitely the third median because it passes through the centroid, and by definition of the median it continues and cuts the segment or the side facing the point M at its midpoint, and that's why MJ cuts AC at its midpoint. We finished that training exercise, and as I promised you, by the end of the video there is a bonus information concerning a square and an equilateral triangle. Let's go ahead. Let's get started. Notice that in a square, here of course we have a right angle, and here the sides are equal because all sides of the square are equal. Then that square is divided into two equal right isosceles triangles. Now if the side of that square is 6, who can guess what is the measurement of the diagonal of that square? So if the measurement of the side is 6, how much is the measurement of the hypotenuse? That's using the property of the hypotenuse of a right isosceles triangle, which is 6 radical 2. So from now on you can directly know the measurement of the diagonal of a square. It's equal to the side times radical 2 because it represents a hypotenuse of a right isosceles triangle. Now let's move to that figure. Here, as you see, is an equilateral triangle. That's one divided in the middle. We'll get a semi-equilateral triangle. The angle here is 60, as we know. The angle here is 90, and the smallest one is 30. It's clear that this is the smallest one. Now, as we know, if the side of this equilateral triangle, for example, is 6, I'm giving numerical examples to make things easier. If the side is 6, then what about that side? Of course, it is 3 because it's in the equilateral triangle, HF is equal to 6 also, and EF is half of HF. Now, what about the height of the equilateral triangle? The height of the equilateral triangle is indeed the side facing 60, which is equal to the hypotenuse, which is the side, times radical 3 over 2. So the properties we can get now is that the diagonal of a square is equal to the side of that square times radical 2, and the height of an equilateral triangle is equal to the side times the side of that equilateral triangle times radical 3 over 2, and those can be considered as properties. Hope you enjoyed this information and these training exercises, and we'll meet later inshallah in more and more videos.